Thanks for taking the time to watch this video. Just a note before we get started that if you're ever interested in any private tutoring through Zoom and Google Meet, I can offer that service. And that would be for chemistry, physics, calculus, and so many other subjects. So please feel free to drop me a line if you're interested. We can move on to the problem now. You might want to pause it and reread it to yourself, but we're going to begin by looking at the first experiment. Now, that experiment said, if we choose the right font, that 1.5 grams of a sample of our unknown compound was completely combusted in air and 3.52 grams of CO2 was formed. So we have sort of cartoonified that experiment here. We have the unknown compound consisting of carbon in black, hydrogen in gray, and chlorine in green, and then a combustion reaction was done, and in that combustion reaction we formed 3.52 grams of CO2. Oxygen is in red there. And our strategy is to figure out what percent of the original compound, so of this compound, was carbon. So we're trying to find what's called the mass percent of carbon in this compound. And the way in which we can do that is to actually come over here to the product and figure out what mass of carbon is present there. And the reason this works is because whatever mass of carbon we started out with would be the same mass of carbon in our product. This is a conservation of mass concept. So for example, if we started out with 0.7 grams of carbon in the original compound, we're going to get 0.7 grams of carbon in this product over here. But how do we find the amount of carbon present in this 3.52 grams of carbon dioxide? Well, that's the calculation that we're going to do first. So we're going to take 3.52 grams of carbon dioxide, and what we're going to do first is convert that into moles of carbon dioxide. Now to do that, we use the molar mass. So 1 mole of carbon dioxide is going to equal 44 grams of carbon dioxide. Now, if you're wondering where did that 44 grams come from, you would go to your periodic table, you would look up the mass of carbon, which is 12, you would look up the mass of 2 oxygens, so that would be 2 times 16, and that would be 32, and if you add 12 to 32, you get 44. So that's where the molar mass of carbon dioxide came from. Now, that's nice. That gets us the moles of carbon dioxide, but it doesn't tell us the grams of carbon. Remember, that's what we're trying to figure out right now is the grams of carbon. So we're going to do another conversion here. And if you look at the formula for carbon dioxide very carefully, you will see that for every 1 mole of carbon dioxide, you would have 1 mole of carbon. That is simply because looking at the formula, you can see there's a little subscript of 1 in the formula for carbon dioxide. So let's state that again. For every 1 mole of this molecule, you're going to have 1 mole of carbon. Pardon me. So we can write that down as follows. We can say 1 mole of carbon dioxide would give us 1 mole of carbon. And then finally, we can convert the moles of carbon into grams of carbon. We just noted a moment ago that the molar mass of carbon is 12, so this just means that 1 mole of carbon would give you 12 grams of carbon. Now, let's pause and just make sure that the setup makes sense to everybody. The grams of carbon dioxide are going to cancel because they are arranged diagonally to one another, so we're going to go ahead and cancel those out. Similarly, the moles of carbon dioxide are arranged diagonally, so those are going to cancel out. And then we have the moles of carbon arranged diagonally, so those will cancel out. And we are indeed left with the grams of carbon. So let's go ahead and calculate that. And when you do that, you will get 0.96 grams of carbon. So again, let's understand what this all means. So in the CO2 that we got in the combustion reaction, there was 0.96 grams of carbon, but that carbon came from the original substance. So what we're going to do next is we're going to say, okay, well, the original substance also contained 0.96 grams of carbon. What is the mass percent of carbon in that formula? So to get the mass percent of carbon, we would take the grams of carbon, which was 0.96 grams of carbon, and divide that by the total mass of 1.5 grams. And then multiply by 100. Don't forget to multiply by 100. And when you do that, you will get 64% carbon. So that's a good step forward, because that means in the original compound, 64% is carbon. And it's a number that we're going to hold on to, so we'll put a box on it, but we also need to find other mass percents in order to proceed here. So we go back and we read the experiment, and in a separate experiment, the chlorine in a 1 gram sample of the compound was converted into silver chloride, particularly 1.27 grams. So let's set up a little cartoon to represent that. Now, this is going to be a very similar concept. What we're going to try to do here is we're going to try to figure out the number of grams of chlorine in the 1.27 grams of silver chloride. And whatever grams of chlorine we obtain will be the same number of grams of chlorine in the original compound. So again, very similar to what we just did. Let's start out with the 1.27 grams of silver chloride, and we're going to convert that into moles of silver chloride. So 1 mole of silver chloride, and we're going to go look up the molar mass now, is 143.4 grams of silver chloride. Again, we just use the periodic table for that calculation. If you look up the mass of silver, you would get around 107.9. That's for silver, and then chlorine is 35.5. So you just add those together to get the 143.4. So next, we're going to convert the moles of silver chloride to moles of chlorine. So think about, when you look at the formula, you can see that for chlorine, the subscript is a 1. So that means for every 1 mole of the compound silver chloride, we would have 1 mole of chlorine. So that gets us into moles of chlorine. We want grams, so we're going to do one more conversion here. We're going to say that 1 mole of the chlorine is the 35.5 grams of chlorine, and that mass again just comes from the periodic table. So again, the way in which we've arranged all of the conversion factors is that the moles and grams of everything cancels except for the grams of chlorine, and that's what we want. So let's go ahead and calculate the grams of chlorine. And when we do that, we get approximately 0.314 grams of chlorine. So that is how many grams of chlorine is present in the combustion product, or whatever reaction they carried out here. So it's 0.314 grams of chlorine, but that means in the original compound, that 1 gram sample, that also contained 0.314 grams of chlorine. So now we're going to get the percent by mass of chlorine in the original compound. This is quite straightforward. We just take the mass of the chlorine in the original compound in that second experiment and divide by the total mass and then multiply it by 100. Now, in this case, it's kind of easy to see that that's going to give you 31.4% chlorine. So this is great. Let's kind of summarize what we know so far. We have the percent of carbon. We also have the percent of chlorine. What we do not yet have is the percent of hydrogen, but we can easily calculate that because altogether these percentages have to add up to 100%. There is, after all, only carbon, chlorine, and hydrogen in the formula. So to get the percent of hydrogen, we just subtract our 2 percentages that we've obtained from 100%. And when we do that, we get about 4.6% hydrogen. So far, so good, but we still don't have the formula of the unknown compound. We only have the percentages by mass. But we're getting very close to coming up with this formula, because the next thing we're going to do is we are going to take our unknown and we're going to assume that we have 100 grams of the unknown. Now, this procedure would work if you used a different mass. You don't have to use 100 grams, but 100 is usually chosen because that allows us to change these mass percentages very quickly into grams. Because if you have 64% mass of carbon in a 100 gram sample, then you have 64 grams of carbon. And then similarly, if you have 31.4% by mass chlorine in a 100 gram sample, you'll have 31.4 grams of chlorine. And by the same reasoning, we're going to have 4.6 grams of hydrogen. Now, all we need to do is convert these into moles. So let's set up those conversions. So there are the conversions. Again, we're just using the masses from the periodic table for each of those 3 elements. When you perform these calculations, you're going to get 5.33 moles of carbon. You're going to get around 0.88 moles of the chlorine, and then of course you're going to get around 4.6 moles of hydrogen. This is very close to the right answer, and theoretically we could even write the answer as carbon with a subscript of 5.33. We could say chlorine has a subscript of 0.88, and then we could say hydrogen has a subscript of 4.6. Those would be the molar ratios, but we typically want our molar ratios in whole number form. So the technique to get a whole number form is to divide each of the number of moles by the smallest number of moles. We can see that the smallest number of moles is the 0.88. So you come in here and you divide everything by 0.88. And when you do that, you will get approximately, you won't get exact whole numbers, but they're going to be extremely close, probably due to experimental error. And when you do the first one, you're going to get approximately 6. The second one would be exactly 1, of course. And then the third one is going to be pretty darn close to 5. If you want, you can put a 1 there, but that's optional. So that would be the empirical formula of the unknown compound. And if you want to write it in a more conventional manner, you would actually put the chlorine last. So you could write it as C6H5 and then Cl. So that would be the final answer.